So the speaker of the next talk is Ju-Chi Lee, right?
Yeah.
Ju-Chi Lee, he's a senior research scientist at ByteDance. He works on building robust and scalable streaming system for large-scale video applications. So he's going to talk about this TLadder optimization within ByteDance.
Okay. Yeah. Thank you, Professor Han, for introduction. Yeah. Can you hear me?
Yes.
Okay. Yeah. Hi, everyone. My name is Ju-Chi, and I'm from ByteDance. Today, I'm glad to present TLadder, a system that uses client-side information to generate optimal video bitrate ladder and maximize the QoE for video streaming. This work is done by my team at ByteDance and launched globally on TikTok since last year. Most video streaming platforms nowadays use adaptive video streaming, ABR, to stream video content to users. In ABR, the server actually maintains multiple representations of a video at different resolutions. The client side runs the ABR algorithm, which dynamically selects each chunk's representation based on the network condition and other factors. All representation actually forms the ladder. So you can imagine that when the network condition is good, the ABR climbs up the ladder to pick a higher resolution, and when the network is bad, the ABR climbs down the ladder to pick a lower quality. Also, each representation is actually not only defined by the resolution, it's a set of parameters such as resolution, codec, CRF, and others. So let me show you a demo to showcase the importance of ABR. Recall that ABR algorithm actually determines each chunk's representation. So here we visualize the player's buffer, and each slot can store a chunk, and each chunk takes 1 second suppose. And the height of the chunk is its bitrate. And now we assume we have a poorly designed ABR algorithm that only gets the highest quality resolution, representation. Then the problem is, if the video bitrate is consistently higher than the network bandwidth, then the consumption rate of the buffer will be higher than the replenish rate. So eventually, the buffer will become empty and the video will stall. There is rich literature on ABR in the past decades. For example, some algorithms try to predict the throughput and adjust the bitrate accordingly. Some use the buffer level as an indicator. And some solve an optimization problem to determine the best representation. And some work use DNN and use reinforcement learning to make the ABR decisions. Recall that a ladder is all representation that's stored on the server, and the ABR logic can only select the proper representation within the ladder. Therefore, ABR impacts the ladder actually impacts the ABR's decision. In the modern UGC platform like TikTok, so when a video is uploaded, it will be transcoded to multiple representations according to the ladder configuration. Each representation is a specific set of encoding parameters in the configuration. So at TikTok, we have a dedicated service that generates such kind of configuration. Since there is a rich literature on ABR in the past 10 years, so the room for ABR to improve ABR itself is actually probably limited. So at the same time, the ladder generation is equally important for video streaming platform, but it receives much less attention compared with ABR. So the room for improvement could be larger. So in this research, we studied the ladder optimization problem. We answered 3 questions. First, how to evaluate a ladder? Specifically, how can we determine a ladder is good or bad, or how can we compare 2 ladders? And we will introduce a quantitative metric we use to evaluate ladder. And the second, how to generate the optimal ladder. We will cover the system and algorithm design to obtain the optimal bitrate ladder. And third, how much gain a good ladder can bring. We will show the results from both the A/B experiments and the trace-driven simulation. So let me further motivate the problem a little bit more. So why ladder matters for us? First, TikTok serves all the users from all over the world, and the network infrastructure differs across the countries. In countries with good network, we want to have more high-quality representations in the ladder so that we have a better watching experience. And while in countries with a poor network, we want to have more low-quality representation for playback smoothness. So the takeaway is we need to use different ladders in different areas. And the second reason is videos are also different. So here we pick two videos. One have a simple content and another have a complex content, both at 1080p. We plot their encoding characteristic curves, and the x-axis is a video bitrate, and the y-axis is the video quality score measured by VMAF. And VMAF is an objective video quality metric, and please remember this metric. We will use it later. So in this curve, by tuning the encoding parameters, we can actually achieve different trade-offs between bitrate and video quality. We can see that in order to achieve the same quality, we need to use different encoding parameters for the two videos. And the complex video actually needs a much higher bitrate than the simple one. So we make the similar observation on the other resolutions. So the takeaway is we also should use different ladders for different videos. The third reason relates to the computational resources. If we enumerate all the combinations of encoding parameters, there will be hundreds or thousands of representations. But it is impractical to transcode all of them because transcoding a video needs computational resources. And the video transcoding is one of the largest resource costs for video platforms. So typically, we can only transcode less than 10 representations in a ladder. So the takeaway is we need to strategically pick those small amount of representations from a large number of candidates. So now let me formulate the ladder optimization problem. So given m candidate representation of a video, so we want to have a subset of n representations that maximize the QoE, where L in is the total candidate representation, and L out is the output ladder. QoE Vs is the QoE of video V transcoded by the ladder S. We empirically define the QoE as a linear combination of three terms. The first is the video quality measured by the average VMAF, because everyone wants a high-quality video. And the second is the rebuffering penalty. And the third is a data usage penalty. So because streaming a high bitrate video costs the bandwidth, and the bandwidth means CDN costs for the streaming platform, and also mobile data usage costs for the users. So the optimization problem needs to be solved on per video basis because we generate ladders video by video. So a brute force search for all the combination actually doesn't work since it has an exponential complexity. So our solution is based on dynamic programming. It can be proved to be optimal and has a polynomial complexity. So for the detail of the algorithm, please refer to our paper. But when solving the optimization, a key point is to calculate the QoE. So remember that QoE Vs means if the video V is transcoded using ladder S, what is its QoE on all the users in the target region? So as we define, QoE is a linear combination of the quality, rebuffering, and data usage penalty. We found it's difficult to model QoE analytically, so we take a data-driven approach, which estimates the QoE using big data. Next, I will showcase how to estimate the quality term only in the QoE function, and estimate the other terms follow the similar ideas. So to estimate the quality, the idea is to calculate the average VMAF score across all users' play sessions. In another word, it is a weighted average on VMAF of all representation in the ladder. And the weight is each representation's play probability. So let me explain this formula in a little bit more detail. Here, VMAF, VSJ, is a VMAF of J's representation in ladder S. It is calculated from a lightweight ML model which predicts each representation's VMAF score and bitrate without performing extra transcoding. Next, from big data, we obtain the network speed distributions and discretize it into bins. Here, Pi is the play probability of ith network speed bin. The network speed actually also affects the video bitrate selected by the ABR algorithm. Most ABR algorithms do not use a fixed mapping between network speed and the video bitrate. Instead, it will be a probability distribution. So we estimate the video bitrate distribution for every network speed bin using the playback data in the past. Recall that we have the predicted bitrate of each representation. So we plug the predicted bitrate into a CDF. And we calculate the play probability of each representation in the particular network speed bin. And this is QIJ in the formula. Together with Pi and QIJ, we have the joint distribution of having speed bin I and viewing the representation J. It serves as the weight to calculate the average VMAF. So its underlying distribution are obtained from billions of users' playback data. Also, a performance optimization here is we can rewrite the formula in a matrix calculation form so that we can use some hardware technique to speed up the calculation in 10 times. Now let me describe the overall ladder optimization system called TLadder. So here we first have an optimizer. The optimizer runs the dynamic programming algorithm. And then for each candidate ladder S, it asks the digital twin simulator to calculate the QoE. The optimal ladder configuration is then passed to the transcoding engine, which performs extra transcoding tasks to generate the ladder out. And the ladder is then consumed by the client that running ABR algorithm. And client uploads the play statistics like network speed, rebuffering rate, playback bitrate to the data lake. And the data is then aggregated and processed used by the simulator for data-driven QoE calculation. There is also a separate video analyzer that generates the predicted VMAF and the bitrate. And the optimizer and the simulator together form the core TLadder system, and the TLadder logic is triggered whenever there's a new video uploaded. So we implement the TLadder system on TikTok's production system. And since its launch in 2024, it has produced a ladder configuration for more than 60 million videos. And we conduct global scale A/B experiments. And the control group is called VLadder, which is our legacy ladder system. There are three key differences between VLadder and TLadder. First, VLadder conducts a brute force search on limited number of the representation combinations. And second, given a high search overhead, VLadder only decides ladder on per region basis instead of per video basis. And third, VLadder does not use the playback data for QoE calculation. We perform A/B tests in two regions, a developed region and a developing region. Both regions has more than 100 million daily active users. So here are the results. So we first present results for the developed region. The figure shows the overall QoE and the three micrometrics, video quality, rebuffering ratio, and the CDN cost. So usually, under these dimensions incurs trade-off. Like if you improve the quality, the rebuffer will also increase, and vice versa. But the TLadder simultaneously improves the QoE, VMAF, and reduce the rebuffering compared to VLadder. And TLadder does not incur any additional CDN costs. And we also make the similar observation for the developing region. So we also compare the TLadder with other laddering systems in the literature, including those from industry like Google and Brightcove, and those from academia like Aristmeus. The result is produced using trace-driven simulation, and each algorithm is corresponding to a specific marker type in the figure. And we also twist the tunable parameters in each algorithm to explore different trade-offs between rebuffering and the video quality. So each point in the result is generated by an algorithm plus a set of parameters. So ideally, we want the ladders to fall in the lower right corner, which have a higher quality and a lower rebuffering ratio. We can see that TLadder can actually outperform all those ladder systems in balancing those trade-offs. So in summary, in this work, we propose, so to summarize this work, actually, video ladders impacts the ABR's decision and plays an important role in video streaming. And ladders need to be generated for each region, each video, under the specific transcoding cost. To derive the optimal ladder, we propose the TLadder, which establishes a principle, the QoE-Centric optimization framework. It uses both video information and large-scale playback data to make the ladder decisions. It can simultaneously improve the video quality and the playback smoothness compared with the state of art. For future works, one direction could be the co-design of ladder and the ABR system. On the other hand, current TLadder requires a massive data feedback that is only accessible for big companies. So another direction could be improve the data sampling efficiency so that the ladder could be generated with a much smaller data input. That concludes my talk. Thank you for listening. Yeah, I'm happy to take questions.
Question?
Thank you very much for the wonderful talk. One question, just want to clarify, with your TLadder results, is that going to be different ladder per video content or even different ladder per video content and network conditions and regions, you know?
We create different ladders on different videos plus different countries. But we assume the country has its own, countries have its own net throughput distribution, network throughput. Yeah.
Gotcha.
Thank you for your talk. My question is about the QE model that you used for measuring the QE. Which QE model did you use for measuring these results?
Your question is Lin-Xi model?
About the QE equation model.
Yeah, so we follow the standard QoE calculation in the literature. So,
Linear combination of the three. He had a slide on that, right?
Yeah, the name, but because we have many QE models, the linear combination of that. But the next one is that, did you design this system for the live streaming or for the VOD?
VOD system, yeah.
Oh, okay.
Okay, the question from the back.
Ricky from CADA. So actually two questions. One question is that because the standard stash, the transcoder only transcode the video once, right?
Yeah.
And then it's cached in the CDN cache or wherever server. But it seems like you have a live decision of transcoding. So I'm wondering how much overhead to the transcoder, or will the transcoder become a bottleneck of delivering the video? So the second question is that because for static ladder, it's very easy to cache the CDN. So when you generate this ladder in live, so it will impact on the hit rate of the CDN cache.
I think I only get your first question. So basically, we can discuss the second question after the talk. So basically, what we do the transcoding is, because transcoding itself actually consumes a lot of resources. So as long as the laddering system does not surpass the resource of the transcoding itself, we should be good. So actually, we did some micro benchmark. It only consumes maybe less than 0.1% of the resources compared with transcoding itself. So the bottleneck still in the transcoding the video out itself, and we only at a very marginal cost.
Time for Winnie's final question.
Yes, actually, together with Farzad, who just asked a question, I'm a co-author of the Artemis paper that you evaluated. Right, so actually Farzad asked about QoE model. And actually you did show it, but it was a bit strange because there are three terms, and the last term you subtracted the bandwidth. right?
Period.
Yeah, so I think I understand if you want to minimize bandwidth as a constraint, but by itself, it's kind of doesn't seem to be very reasonable, right? The more bandwidth you allocate, the higher quality of experience will be. So it was kind of, I don't know, a strange take on the classical QoE models, right?
I got you. I got your question. So, and there is a small difference, which is the last term in the QoE definition. The reason we do that is we tried the term without the last one before, and it turned out the result is not good. We analyzed the result and we found that it's kind of some users hate to spend too many data plan on the video streaming platforms. So if we consume their too much data plan, and they will actually don't watch the videos anymore, or maybe directly quit. Yeah. So that's one reason. Another reason that's because the data usage actually costs money for them, and also costs money for the platform, because if you in platform we have to when we stream the content to users, we also pay money. So we combine these two together as the last term.
And maybe another very quick question. So Artemis is a dynamic bitrate ladder which changes during the video streaming session. And in your case, you get this feedback from the clients, but you seem to have the same bitrate ladder during the session, right?
Yeah, so the feedback is actually calculated on daily basis. It's not per session, it's aggregated for a larger number of users on the historical data. So it's not because we do the VOD, we are not doing the real-time streaming, so that could work, and which differs from Arithme's case. Yeah, a little bit.
Understood, thank you.
Yeah.
Yeah, let's thank the speaker again. Thank you. Thank you for all the great interaction. So.